Hello, this is another recording, and this one will deal with assessing process capability. This is an activity that takes place both in the measure phase and in the end of the improve phase when we want to demonstrate the potential capability of our new process. So in this section we'll talk about what process capability is, how it's currently assessed, and I'll give an example. I will not discuss every slide in these notes. I do recommend you at least read them before listening to the video, but I will capture the highlights of the discussion. Okay, we're in slideshow. Okay, and recall we talked about in the SPC section how a process being stable is not necessarily a measure of capability. That is, a stable process or in-control process can very well be very consistent in poor performance, but it's consistent at it. So stability tells us nothing about performance, which is typically measured in terms of a customer, client, or patient needs. So process capability studies, and we're going to discuss one specific approach to it, are a way to try to at least specify how capable the process is, usually with respect to some sort of specification limits or specification requirements placed on the process. Okay. And very simply, I use the piston ring manufacturing example from SPC. And so here we have an example of 1,000 rings that have been measured. And we see that the average is about 70.001, which is essentially on target because the target for the process is 75 millimeters. Okay. Is the process consistent? Well, this is what becomes a difficult question. Basically what you do, you take the distribution of the process and you compare it to the specification limits. And then you look at the probability, or for raw data, the percentage of observations falling outside of the limits. So in saying if a process is consistent, we usually think in terms of the percentage of observations falling outside the limits. And remember, in what's called a Six Sigma quality level, that would amount to nothing more than 3.4 part per million outside of the boundaries. In this particular process, it's hard for you to see, but the blue lines are the specification limits, and about 5% are outside of the limits. By automotive manufacturing standards, this would be considered a highly incapable process. They can actually be even more stringent in quality than a Six Sigma quality level. They may want better than 3.4 part per million defects. And finally, we'll mention this because it's important, we also have to take into consideration the shape of a distribution. So most process capability measurements assume a normal distribution, and in our piston ring example you can see from the histogram that the distribution is more or less symmetric about the mean. It's normal looking. If it is not normal, then most of the methods that are currently used simply do not work correctly, and it's really beyond the green belt level to get into what one might do to assess capability if the response or measured characteristic is not normal. So basically, when we talk about process capability, the usual approach to assessing capability are what are called capability indices. These are not without controversy, but they are also widely used in many industries. Also, I've seen them used in transactional or non-manufacturing processes. So process capability studies are designed to collect data to assess capability, and it's usually done in terms of the capability indices, which I will explain. Okay. And I will mention we're only going to talk about continuous characteristics. Okay. Let me open up a pen option here. So basically, we're going to talk only about continuous measurements. For nominal CTQs, we typically talk in terms of proportion defective, which is often turned into a part per million defect. So our focus is on continuous. If you have something nominal, such as the only measurement you can make is simply something passes or failed, or is a success or a failure, and so forth, then we have to talk in terms of part per million. Okay. As I said, I won't talk about every single slide. And we've mentioned earlier on a number of occasions that typically we can define a normal distribution, okay, in terms of plus or minus 3 standard deviations of the mean. Basically, that covers 99.73% of a normal distribution. So a process that we would consider barely capable, okay, this would be sort of a minimum, the plus or minus 3 sigma window would just align with the spec limits. And in fact, such a process would deliver about 2,700 parts per million defect rate. Again, this may sound good in some industries like automotive and aerospace, and even like electronics. This is typically not considered capable. So basically, when we talk about capability, as I said, we'll assume a normal distribution, and we'll define that normal distribution by that typical plus or minus 3 sigma window of the mean. Okay. Well, so what do we mean by 6 sigma quality level? Well, the original definition of it was actually, believe it or not, a 12 sigma window. In other words, it's 6 sigma to each spec limit, and this would amount to 0.002 part per million defect. In point of fact, that is so small it's actually not even measurable. So how do you measure improvement if you can't even quantify your present capability? So in a controversial move, some people at Motorola, where 6 sigma began, decided that, well, instead of 6 sigma, we'll assume the process can shift off target 1.5 standard deviations. Okay. Unfortunately, they only considered it shifting in one direction. So here, the process is shifted off its target in the direction of the upper spec limit by 1.5 sigma. This means that the closest spec limit is 4.5 sigma. So that's 3.4 part per million defect, and this is actually how they define 6 sigma quality. So that's where the 3.4 part per million come from. This 1.5 sigma shift has never been justified, and it appears to have been a convenience. We don't really work, in fact most people don't really pay attention to sigma quality levels anymore, but given this is a 6 sigma course, I wanted to explain the history of it. So what we call 6 sigma is actually 4.5 sigma in actual practice. Okay. So basically, I'm going to skip through a few slides, and I just want to mention quickly that a danger in specifying a hard number as specifying acceptable quality. For instance, if we said 3.4 part per million is the definition of a 6 sigma quality company, well, I would point out for a commercial airline company, 3.4 million crashes, crashes per million flight hours would be a nightmare. They burn through 1 million flight hours very quickly. So 3.4 million would be totally unacceptable. Or if you're a company that makes inexpensive plastic Easter eggs, would you really care about 3.4 part per million defect rates? Knowing a little bit about those industries, quality is hardly a primary concern on something that has got to be cheap and a commodity. So my message is what acceptable quality is should really be driven by the application. I'd also argue there are a lot of areas in the healthcare system where 3.4, say, let's call it errors or defects per million, might not be acceptable. As a matter of fact, for instance, credit card transactions, which go into the billions, even in some cases worldwide daily basis, 3.4 errors per million transactions would be unacceptable. Okay. So what are process capability indices? Okay, I'm just going to give you an overview of them. They're straightforward. They are not necessarily the greatest idea, but they're widely accepted, so you should be familiar with them. Well, here are some assumptions you have to make. These are essential. Number one, stability. Okay. Process capability implies that you can predict the total amount of future variation. Okay. A process that is unstable, the amount of future variation is unpredictable, therefore it really doesn't make sense to be talking about process capability, because any capability you assess or assign is an artifact of the time period in which you made it. Another assumption, this is another quite strong one, the distribution of the CTQ must be approximately normal, and this is a fairly strong assumption. The observations themselves must be independent. This is a bit of a problem. By the way, this is very hard to assess, and we won't get into it. It simply means every measurement you take is uncorrelated with every other measurement. Most of the time, this can be a reasonable assumption, and in a black belt level course, we might talk about assessing independence, or what we call autocorrelation, that is, data correlating with itself. And finally, there's another problem that people don't seem to understand. The specification limits must be symmetric about a specified target. So if you have two-sided spec limits, upper and lower, they must be symmetric, or these indices do not work at all. Okay, so what are the common indices? Well, I'm only going to talk about the most common ones, and frankly, there is volumes of literature on these indices. Mostly people in academia discovered this was an area where they could do relatively small amounts of research and publish. So the topic of process capabilities has been beaten to death in the literature. Basically, we're going to talk about what's called CP. That's the original process capability measure. CPU for a one-sided spec, and CPL for a one-sided spec, and CPK for a two-sided spec. CP simply compares the distribution to the spec limits and does not take any account of whether or not the process is off target. CPK, on the other hand, assigns a penalty for the process being off target. So basically what we're doing, and I show you the CP calculation on slide 16, is we just compare 6 sigma, and remember 6 sigma defines one normal distribution. So we divide one normal distribution into the spec range to see how many will fit within it, and that's called CP, and the process need not be on target. That's not even taken into account. Okay. CPU measures capability against an upper spec limit. Since it's only measuring the right-hand tail of the normal distribution, instead of dividing by 6 sigma, we divide by 3 sigma, but it's the same idea. How many normal distributions would fit between the mean of the process and the upper spec limit? Okay. And then CPL is a lower spec limit, and CPK is the minimum of the two. So CPK accounts for off-target performance by simply using which of the two one-sided capability indices is smallest. This was believed to be a worst-case scenario. We will not get into the details, but in actual practice, CPK doesn't actually capture, or doesn't truly bound the worst performance, but it's a well-accepted measure of off-target capability performance. And on slide 19, I just give you a simple hand calculation. I won't go through the details. You can take a look at it. And then for practice, I give you the same problem on the next slide, and we'll leave that to the interested viewer to go ahead and try it. Okay. So basically, what is CP and how do you interpret it? Well, as I said, what CP measures is the number, and basically CPK does the same thing, again allowing for off-target performance. How many normal distributions will fit between the spec limits? Remember, I said, a CP of 1 is considered minimally capable, and that's really a reasonable requirement. A CPK of 6 would be considered absolutely outstanding performance and would imply that you could fit 6 normal distributions between the spec limits. In order for this to be possible, the amount of variation in the process would have to be very small compared to the spec range. Okay. So what are acceptable values of CP and CPK? The answer to that is who knows. In fact, again, as I mentioned about risk, I think the risk assessment, which is how CPK is sometimes used, it depends on your industry or your application. Joseph Juran, who wrote and I mean this, the handbook on quality, and was considered one of the quality gurus along with Edwards Deming. By the way, Deming and Juran despised each other. It was fascinating. They had very little use for each other. I guess each had an ego that was just too big for them both to fit on the same stage, which is basically true. He said 1.33, and he basically introduced the idea, but there's no rhyme or reason to that. Motorola, as part of Six Sigma, said 1.5. The automotive industry typically says a minimum of 1.67 with continuous improvement beyond that. Okay. And again, I just throw these out there. I don't subscribe to specified values. I think it totally depends on your application. Okay. Okay. There we go. So the problem, I've just shown you the theoretical formulas, and in them you saw the theoretical mean, mu, of the distribution and the theoretical standard deviation, sigma. These are parameters. We typically have no idea what the theoretical mean is or the theoretical standard deviation, so we have to estimate them. And this has historically led to some confusion as to how do we assess or estimate the standard deviation. And the Automotive Industry Action Group, AIAG, and they more or less write guidelines for the automotive industry, and they actually a fairly powerful group, and they created what they called the short-term and the long-term estimate. Frankly, and I know this for a fact, in their original handbook published in the 1980s, they got this totally confused. have kept people confused since, and I'll simply make the statement that even they're starting to back away from the idea of short-term and long-term variation. But we need to discuss it because many people using this still talk about a short-term, in other words, looking at the capability in the short term, looking at the capability in the long term. Okay, so where do we get a short-term estimate of the standard deviation? In fact, what do we even mean by it? Well, traditionally, short-term is based upon rational subgroups from SPC, and we discussed those in the SPC sections. So they estimate the standard deviation within each subgroup and then pool it together, as I showed for SPC, and that's what they call short term. Okay, long term, since there's really no simple definition of what long term means, they simply take your entire sample of data and calculate the standard deviation over the whole data set, and the long term ignores the idea of a rational subgroup. Well, here's the issue. Remember, I said in order to use capability indices, you must assume the process is in control, that is, stable. If a process is stable, the total amount of variation in the process is consistent over time. Therefore, there is no difference between short-term and long-term variation. This was never thought out very well right from day one. If the long-term variation, in fact, is much larger than the short-term, the process is unstable. If the process is unstable, the future capability is unknown in any case. So basically this is somewhat artificial, but we do need to explain the difference to you. Okay, so basically when we estimate the capability indices used in industries, I keep conflating the words, we simply plug the sample estimates into the formulas. So mu and sigma are now replaced by their sample estimates. I mean, this is virtually what you have to do. And it turns out, once you plug the estimates in, the standard deviation and the sample average, CP and CPK are terrible estimators. We aren't into statistical theory in this course, but in theory, if a group of statisticians got together and tried to come up with the worst possible estimate of something, CP and CPK would have to be at the top of the list. I am quite critical of them when I teach this material to people and warn them, be careful about taking these statistics too literally. Basically what happens is, because you're estimating the mean with X bar and the standard deviation estimates sigma, from sample to sample the CPK is highly unstable. It wildly varies even for a process that is in a state of control. Okay. So that's the problem with them. You estimate a CPK, but the estimates are wildly varying from sample to sample. Therefore, one has to be careful not to make a literal interpretation of these estimated indices. That's one of the biggest problems. People who use these indices fail to understand that they're estimates, and they tend to view the estimated capability indice as some sort of a constant. In other words, they accept it at face value. The point is the actual capability is highly variable. In fact, very difficult to know what it is with any precision. Okay, so we're going to illustrate capability, and we'll show how to do it in JMP using a data set called CLIPS2 that is located in the JMP sample directory. There are two places in JMP where you can do capability. Okay, one is in the distribution platform, The other is through control chart, and I mostly use control chart to do it. So this data set is from a manufacturing process where they manufacture clips, and the key quality characteristic is the clip gap. It must, in other words, gap is too small, clip won't fit. Gap too wide, clip will fall off. Okay. So clip gap is the CTQ. Okay. So I'm going to go ahead and go over to jump, and we'll take a look at the clips data. So this is the clips data, and just to show you where you can store spec limits if you don't want to have to manually enter them, I'm going to highlight the gap column header, right click, and go to column info. Notice one of the column properties that is selected is called spec limits. Okay. I'm going to actually say show graph references. Spec limits as references on graphs, and there are the specifications for the gaps, and notice that they are symmetric about a target of 14.8. Okay, so we're going to go to Analyze, Quality and Process, and go to Control Chart, and this is subgroup data, so I'm going to pick an X bar chart, and it's subgroup by date. So each date represents a rational subgroup. Click on gap, and I'm going to specify that we use standard deviation. Okay, and in the lower right hand corner, click capability, and that turns on the capability analysis. So I'm going to click OK. Notice I get this, well, you could call it a capability dashboard. By the way, if I hadn't stored the spec limits in the column info window, you would have been prompted to add them. Okay. So notice that this is doing something called short-term capability. I'm going to explain some differences here in a moment. First, we look at the control chart. You look at the X bar chart. It looks like a very stable process, so that's important. Then we look at a normal quantile plot. It's a straight line. This is almost perfectly normal, so we've met the stability assumption, the normal assumption, and the spec limits are symmetric about the target. And we'll also notice they give you this nice little graphical display. Based on the histogram compared to the specs, we may be slightly off target. Now notice that they're giving you two different capabilities. Okay, one is called long-term. What long-term does, it just takes all of the data and calculates the standard deviation. Okay, if you want to see that, I'll click on gap, and under display options I want to see summary statistics. Okay, so the standard deviation is 0.2582, or sorry, 424. There you go. That's where they got it from. Then they give you control chart, which is short-term sigma, and notice that sigma is slightly different because this is actually taken from the average for the S chart. In other words, this is the average of the subgroup standard deviations. Notice they're not too different. In fact, it's kind of interesting. The long-term one is slightly smaller. Well, that's because this is a stable process, and any differences between the two are purely random. There's really no difference. And look at the short-term CPK. Okay, 0.962. So this would indicate that if at most we are barely capable. Okay. Now notice under long-term, they're using this notation PPK. That's based on the AIAG terminology, which again is just totally confused people. They often get this backwards. And the long-term CPK, they call it PPK, same thing, is about the same. And then they give you this thing called a confidence interval. We won't get into interpretation of that right now, but what that means, we are 95% confident whatever the true CPK is, it's somewhere between 0.84 and 1.14. Actually, it's a fairly complicated calculation for CPK, so I won't get into it. So our conclusion would be that this is actually not a capable process. And notice JMP also, for people who want it, give you a sigma quality level, and it's 4.4. So we're definitely below 6 sigma. And they also give you the ppm rate, which I can tell you again, for many industries, this would be unacceptable. The defect rate is too high. Very quickly, you will not get this PP notation by default. You have to go to the Preferences menu in JMP. Okay, so you go to the Preferences menu in File. So it's in the File menu, Preferences menu. And then under Platforms, go to Distribution, scroll over, and look for an option, if I can get it here for you, PPK labeling. Just check that, and then after that, it will give you the PPK labeling for long term. Again, I don't consider this a major issue. All I would tell you is if CPK and PPK differ by very much, then it's probably the case that you don't have a stable process. This is basically all there is to creating these process capability indices. And I think I'll do one more thing just to illustrate. I'm going to do something called bootstrapping, which is beyond our level of this course. It's a modern statistical technique where we can mimic the idea of repeatedly sampling from a process. This is one sample of one data set. Well, what if I could come back, collect a sample thousands of times, and in each sample calculate a PPK or a CPK? What you would discover if you could keep doing this over and over? You would see this incredible variation that occurs in these capability indices. So I'm going to go ahead and right click in the long-term sigma report. At the bottom of it in JMP Pro is something called bootstrapping. Okay, and I'm going to do 2,000 of them. I don't want to get into all the details. I get into this in some of my other stat courses. And for technical reasons, I'm just going to select fractional weights, click OK. Okay. So JMP is actually mimicking the process of sampling 2,000 times from this process and calculating a PPK for each one of those. And while I am doing this, I want to show you what I mean by these capability indices are wildly varying from sample to sample. By the way, this is time consuming because it's literally going back to the original data table, doing what we call resampling with replacement from the table, meaning some observations get in multiple times, some get in it not at all in any one of the bootstrap samples. That's what makes them all different. That's what allows us literally to mimic the process of repetitive sampling from the same distribution. So we're almost there. Okay. So let's take a look at CPK. So I'm going to analyze distribution and look at PPK. Okay. Notice, even though we had a relatively large data set, look at the range of CPK values, all the way from 0.81 to 0.124. And what JUMP does, it takes the percentiles, the 2.5th and the 97.5th, it takes those two intervals and it constructs what's called a bootstrap confidence limit. In other words, what it's saying is we don't know what the true capability is, but it's somewhere in that interval from about 0.88 to about 0.12. So a lot of variation, so you should never literally interpret one of these CPK values from a single sample. Okay. And the notes more or less explain what I just went through. In long and short-term variation, there's one last example using the pistons data, which I will not do because it literally is the same as what I just did. And so that literally ends our discussion of capability, again based upon the assumption of a normal distribution.